Hi everyone, this is polar area video part 2. This is going to pick up where the first video had left off. I just finished showing you setting up 1/2 integral r squared d theta for both of these, just to show you what each of these would look like for the individual graphs before we try combining everything. There are going to be maybe 2 or 3 or many different ways to set up the area integrals for AP free responses. And oftentimes the way that AP will do it on their scoring guideline is they're going to look at the shaded region area, so like this right here, and they're going to look for the easiest way to do it, which will often involve some basic geometry that you could have done in middle school or 10th grade, and then they'll do a little bit of calculus to get the rest of it. So I'm going to show you method 1, which is going to involve finding a whole area and subtracting part of the area. Then the other method will involve 2 different chunks that you're going to add together. Method 1 involves considering, so we want the shaded region R, and if I look at shaded region R, it's part of this whole green circle here. And I know the area of the whole circle because it's a circle. So area is going to be pi, the radius is 2, pi r squared. Now that is the whole green area, okay? And whenever I do that, it's going to give me this entire thing. And what I want to get rid of is this piece right here. And that would involve area between 2 polar graphs, and that will leave me with region R whenever I'm done. In area here, we are going to consider going from 2 pi over 3 to 4 pi over 3, rotating around this way, and you have to decide what is the inner curve and what is the outer curve. So this here is the outer boundary, or further from the pole. This one right here is the inner boundary, closer to the pole. The outer one is r equals 2. The inner one is 3 plus 2 cosine theta. So what I'm going to do is do an integral from 2 pi over 3 to 4 pi over 3. So make sure you're writing down the setup. And I'm going to do my outer, which is r squared, minus my inner, 3 plus 2 cosine of theta squared d theta. So that involves taking the entire area in green and then taking away the area in orange, which is this piece right here. So I get that jotted down. I'm going to show you another way, which is going to involve 2 separate parts and not subtracting really, but adding this time. So what we're going to do is look for a basic geometric shape to make our lives easier. And if you look carefully here, what we're going to do is we're going to consider this piece right here, which kind of looks like a Pac-Man. And we're going to think, all right, this goes, it's a whole circle, but the part that's taken away is when you rotate from 2 pi over 3 to 4 pi over 3. And if you think about 2 pi over 3 and 4 pi over 3 on a unit circle, 2 pi over 3 to 4 pi over 3 is 120 degrees. What's left here is obviously the 240 degrees, which is 2/3 of a circle. So what we can do is take part of the area, which I'm going to do in blue here. So take this chunk right here, and that part of a circle is 2/3 of it. So 2/3 times pi r squared. So I have this part at least here, 2/3 of a circle. What I still really need is this bit here. Now it's really important to realize that what I'm shading in red right now is not the area between 2 curves, because the area between the 2 curves was this chunk right here. We already used that for the previous method. The area in red is just the area bounded by my blue polar function here from 2 pi over 3 to 4 pi over 3. So if I just add an integral from 2 pi over 3 to 4 pi over 3 of my blue function, which is 3 plus 2 cosine of theta squared d theta, oops, don't forget the 1/2. This right here gives me the area swept out by my polar curve in blue from 2 pi over 3 to 4 pi over 3. And when you combine those two, you're going to get the exact region that you want shaded in gray. You should end up with 10.370 rounded to the 3rd place. And if you type those in your graphing calculator, which I would highly recommend you do, you should get that. If you don't, it means you typed something in incorrectly here. Oh, you know what? I just realized that I'm missing a 1/2 right here. Oops. Okay, you always need the 1/2 when you find the area. I'm going to save the other parts for in-class practice or possibly for your Saturday session, so hold off on those. I do want to do one more polar area function with you, or free response I'm going to do with you. Again, just like the previous one, there are two ways to do it, and there's actually a third way that I found how to do it. I'm not going to do it in the video, but just keep in mind, if you see a different way, it doesn't mean it's wrong. It just means you're viewing it differently, and you could definitely end up with the same thing as I'm going to end up with. Just like last time, method one is going to involve a whole minus a part, and the other method will involve two different pieces that we're going to add together. So let's take a look. Once again, we're only going to do the area part. Part A. We'll save the other parts for in-class practice. Okay, so I have a circle r equals 3, which is this here. And then I also have this interesting polar graph, which looks like this. And this time they don't give me the intersection points. So before you do anything, you're going to have to find your limits of integration at some point. So it'd be really nice if I knew where they intersected. It looks like they intersect here, here, and here. So let's go ahead and find where they intersect. Write this work down, and if you want to sketch the region, I want you to sketch the region and mark it up, but I will give you the free responses next time I see you in class, just so you know. So I'm going to set r equal to r. My 3's cancel. I have 0 equals -2 sine of 2 theta. So 0 equals sine of 2 theta. And you want to find where theta equals 0. That would be a 0, pi, 2 pi, etc. 0, pi, and 2 pi. So that means that if you divide by 2, theta would be 0, pi over 2, and pi. So like your picture here, and see if that makes sense. We're starting our rotating right here when theta is 0. So there's 0. When I rotate around to pi over 2, they intersect, and when I rotate around to pi, they intersect. So these look good to go. They make sense. And if I'm going to find the area, one way to do it is to think about, okay, how can I view my whole entire region here? This is region R. What if I look at my green curve here? And what if I find this whole entire area of the green curve? So the whole area that the green curve sweeps out. And then what if I omit this area right here, which is an area between two curves? Let's try that way. The whole here. Oh my God, touchscreen. The area of the whole will be the integral. And if I want to get this purple region, which is the whole entire thing, I start my rotating at 0. And I go all the way around until I get to pi. And that's going to be 1/2 of r squared d theta. So that right there is in purple. Now what I want to do is get rid of this piece right here. So I'm going to do a big subtraction. And all right, to get that piece that I just shaded, it looks kind of orange now, that is the area between the two curves. The outer one is in green. The inner one is in blue here. And that chunk right in the middle starts at rotation of pi over 2 and ends at rotation of pi. So pi over 2 to pi, and I want outer minus inner. So outer in this case is the green one, and the green one is 3 minus 2 sine of 2 theta squared. I'm going to put my 1/2 before I forget. So that's r squared minus, I'm going to do another r squared. The inner is part of my circle. And do I have enough parentheses? Now I do. Now I do. All right, there you go. So that right there is what I did in yellow and purple there. Okay, so pause that, and I'm going to do the other method with you. Looking for a part plus another part. Let's look at our region R, and I want you to look at it closely and see, can you pick out an easy geometric shape that actually wouldn't involve any calculus? And hopefully when you look at it, you're noticing that part of R is this right here, which is a quarter of a circle. And that quarter of a circle has a radius of R, like that. So it's pi r squared, but 1/4 of it. And then it would involve all of this right here, which I haven't considered. And be really careful, this is not the area between two curves, because the area between the two curves would be this bit right here, and I don't care about that, because I want the area enclosed by my green one, which is right here in blue. Whoa. Now it's in blue. So I'm going to add an integral. And okay, what is that rotating from? It's rotating from 0 until pi over 2. And all I'm going to do is 1/2 r squared. So I don't need to do any outer minus inner because there is no outer and inner. It's just contained by this polar function. There you go. So no matter which way you do it, you would end up with 9.708 rounded to 3 places for the AP exam. We will do more practice of this. You have, now you should be able to answer all of the problems on the AP exam. Take-home test, I'm sorry, answer all the questions on the take-home test. And we'll practice this a little bit more at the Saturday session and in class. And yeah, enjoy the rest of your break. Bye-bye.